Thank you everyone for coming to this talk. It's very thrilling to be here and quite anxious. First speaker, I think, is always going to be anxious. So, Puma, Falcon, Pitchfork, navigating the Ruby web server landscape. My name is Manu. I'm an engineering manager at Logistics. That's my Twitter handle. And I've been writing Ruby since 2006 or so. So yeah, it's been a long time. But I think this last couple of years have been like really exciting because there are a lot of changes in the ecosystem after a lull, and this is part of it. So let's jump in. Why? Why do we care? Why should we care about the web servers? Like, our focus as developers is typically on the application, but choosing the right web server for your workload and tuning it can pay rich dividends. So in this talk, we will look at Puma, which is the default web server. I think almost everybody in this room probably deploys their applications on Puma. Falcon and Pitchfork, and understand their strengths, trade-offs, and when to use each. Because there is no one web server which is suitable for every single task. So let's start with some history. Mongrel. This was the first stable and performant Ruby web server. Its development stopped in 2008, but its code lives on. The HTTP parser of Mongrel is used by Puma, Unicorn, and since Pitchfork is a fork of Unicorn, in Pitchfork also. So for more than 16 years, the code has lived. The biggest step up from Mongrel to Unicorn was a concept called pre-forking. And now, all the popular Ruby web servers are pre-forking web servers. So what is pre-forking? In this, a master boots the application and then forks the workers. The workers handle the requests, and the master's role is only to supervise. There are primarily two reasons to pre-fork. One is speed. Booting an app is slow. You would have experienced this when you open a new Rails console or run a new rake task. It's going to take some time to boot up. And historically, this was such an irritant that there were solutions such as Spring to speed up the boot time, which contributed to its own problems also. Thankfully, due to how Ruby has progressed and how the hardware has progressed, this is not a really big concern in development, but it's still a concern in production. Once booted, the master process can fork the child workers, and this is pretty much instantaneous. It doesn't matter how many workers you have, you pay the boot speed cost just once. And this is why it's important in production. Because if you're booting like 6 web servers independently, then every web server will pay the boot cost price. But if you boot the master web server once and fork it, the cost is paid just once. The second reason is something called copy on write. This is an operating system mechanism to make memory management more efficient. So it allows child processes to share the parent process memory until one of the processes changes the memory. So until modifications are made, both of them can share the memory. So this significantly reduces the overall memory usage. Say the parent has 300 MB memory usage. And once you fork 2 child workers, each of them will have 300 MB shared memory usage. The total memory usage at this point remains 300 MB. But if you use a tool like Top, it's going to show you that each of these processes is using 300 MB. It doesn't take into consideration the shared memory usage. What it shows is known as RSS, the resident set size. What we need, and a more accurate spec, is PSS, or proportional set size, which is shared memory divided by the number of processors sharing it. So in this particular case, there's 300 MB shared by 3 processors, so the PSS of each worker or each process is 100 MB. And actual memory usage is adding up all the PSS of all the processors, which is going to be 300 MB. Now, most of the tools that you use will not show PSS, but you can get it from the proc file system. Just take a PID of the process, run this command, and you'll get an output like this. The first item is RSS, and the second is PSS. There are tools which will provide this in your APM, so you can make better decisions about how the memory usage is being handled. So, when either the parent or the child modifies the memory, it becomes private memory. Any new memory allocations done by the processors are also private. So it could be that the memory which was shared initially was modified, it becomes private, or the child processors want some new memory, that also becomes private. And PSS in this case is going to be the private memory plus the proportion of the shared memory. So for example, for the parent, the private memory is 100 MB, and the shared memory is 200 by 3, and the total will be 166 MB. And the actual memory usage is, if you just add all of that up, is going to be 800 MB. Or an easier way to look at it is add up all the private memory usage and add the shared memory usage once. So all the current web servers use pre-forking to take advantage of this. So you boot up the master process, master is going to use up some memory, and then once you fork the child workers, it's going to share that memory. So your overall system memory usage is going to be lower than if you were booting up each app independently. So now let's take a look at Falcon and how it works. It's a multi-process pre-forking web server. So in a 4 CPU machine, you can have 4 workers, and all of them listen to the TCP port, the same TCP port, 3000. And when a request comes in, it's going to spawn a fiber. And this happens in each worker. The master does not handle any of the requests. The workers handle the requests always. The next request comes in, it spawns another fiber. And it goes on. There are no limits to the number of fibers spawned. Falcon will spawn as many fibers as there are requests. So when to use Falcon? Fibers are cooperatively scheduled, and only one fiber can execute Ruby code at a time. So Falcon is not suitable for workloads which have a high CPU usage. But if your application has very high I/O, say for more than 80%, then using it is a no-brainer. So this can happen when you call external APIs in your request response, which is something you're told never to do in Rails. But if you're using Falcon, it doesn't matter. Or if you are unfortunately in a microservices architecture and you need to call internal APIs and it takes time, again, Falcon is a great fit for that use case. Or you can deploy Falcon for specialized endpoints. The great thing about Ruby web servers is that they all conform to rack. So you write your app once, and all of them will be able to boot it up and serve it. So if you have an application where certain endpoints are I/O heavy, for example, you're accepting file uploads, or you want to stream files from active storage, this is not particularly suited for either Puma or Pitchfork or Unicorn. But Falcon excels at this. So you can deploy Falcon and serve only those requests to Falcon. So hybrid production deployments are also an option. Now let's look at Puma, the king of Ruby web servers. Again, it's a multi-process, pre-forking web server. And you typically deploy one worker for each CPU again. But Puma also has threads. You can configure each worker to have a fixed number of threads or dynamically spawn threads to serve the request until a certain limit. But inside the worker, it's a bit more complicated. In addition to the worker threads, each Puma worker also has a reactor thread which receives incoming requests, buffers it completely, and places it in the to-do queue for the worker threads to process. The reactor thread will accept new requests only if at least one worker thread is free. Let's see how that works. So if there are 4 requests, since at least one worker thread is free, the reactor thread will accept requests. This particular worker has accepted 2 requests, and the remaining 2 requests are probably accepted by some other workers. And it has placed that in the reactor queue for buffering. So what does buffering mean here? The reactor is waiting for the entire request to be received. That is the headers and the body. And this is typically not a problem. But if you have Puma directly exposed to the internet and you have slow clients, somebody on a very slow connection trying to upload something, for example, then it takes a lot of time for the request to actually be fully received. Then it places in the to-do queue, and then a thread picks it up and works. So let's see how the reactor thread helps. So at t equal to 0, where the t is the time, all the queues are empty, and a worker thread is free. Let's also assume that we only have a single worker here, and we receive a request R1. It's accepted and placed in the reactor queue. At t equal to 3, we receive another request R2. Since the thread is still free, the reactor accepts the request and places it in the reactor queue. At t equal to 5, the request R2 is fully buffered and placed in the to-do queue, while R1 is still buffering. At t equal to 6, thread 1 is processing R2, while R1 is still buffering. If there was no reactor, R1 would have occupied one of the threads and reduced the overall capacity. And that's the reason why Puma has the reactor queue. But reactor is not something that you should depend on, because this is a job much better handled by a reverse proxy such as Nginx. All the slow requests will be queued at the reverse proxy, and it will also be more evenly distributed. So this is to be relied on only if you have no other option. Let's take a look at Pitchfork. It's an opinionated fork of Unicorn for the containerized world. Multiple features from Unicorn, such as PID file management, demonization, hot reload, have all been stripped. And the standout feature of Pitchfork is reforking, which we will explore soon. And Pitchfork and Unicorn should always be deployed behind a reverse proxy like Nginx. It's again a multi-process, multi-worker web server and pre-forking as well. And when requests come in, each request is handled by a separate process. If there are more requests than there is capacity, the request will queue up at the reverse proxy. So this is unlike Falcon, where there is no limit. It just spawns fibers. But since there are fixed number of processes, there's a fixed capacity as to number of requests it can process concurrently. So let's look at reforking. And let's revisit the copy on write example. Each child process has a private as well as shared memory. So what's there in this private memory? You can divide that into two parts. One is private static and one is private processing. So what is private static here? So the master just boots the application. It doesn't run it. When requests come in, it's the worker processes that run the application. So there is going to be a lot of memory usage by Ruby VM to cache the code that is being executed. And if you're using a JIT, such as YJIT, then YJIT is going to have its own memory. And this is part of the private static memory region. And once the application is warmed up, this is not going to change much. And then there is private processing. So this is the memory usage by a request. You load data into active record, you serialize data into JSON or ERB. All that requires memory, and all that is part of private processing. And these objects which take up memory for private processing are not typically relevant after a request is processed, because you don't need the data after the request is done. And these will be typically garbage collected, whereas private static is going to remain there. The key insight behind reforking is that if you fork a warmed up worker, they can share this private static memory also. And only private processing remains private to each worker. In terms of memory efficiency, this will be almost equivalent to creating a thread. So how Pitchfork handles this, if you enable reforking, is it first boots up a mold, which is generation 0, and then all the workers are spawned from the mold. And once enough requests have been processed by the application, and this is configurable, Pitchfork triggers a refork. So it takes one of the workers and makes it the new mold. And this is the Gen 1 mold. And once the Gen 1 mold is ready, the Gen 0 mold is terminated. And then one by one, each worker is replaced by the Gen 1 mold. And this process repeats. After processing 1,000 requests, you will have a Gen 2 mold, and then a Gen 2, it'll be all Gen 2 workers. But after a certain point in time, there'll be no more changes in the private static memory, and you will no longer have any benefit in reforking. And so after processing a certain number of requests, you can stop the reforking. This is not enabled by default. And the reason is that unlike when a master forks a worker, you're forking a warmed up worker. So there could be threads which were running, which have opened sockets, which could get problematic when you refork. And some gems are now incompatible, for example, gRPC, Ruby, WIPs. But if you do not have any incompatible gems and you're sure that your code can handle reforking properly, then it's a great tool to reduce your memory usage. And Pitchfork also provides hooks so that you can handle your thread connections, etc. after you refork. So why Pitchfork when you have Puma? Reason number one, it'll provide you the lowest latency. And for that, we have to consider how GVL works in Ruby. Let's consider two requests. Each have varying I/O and CPU usage, but the total time taken by each, if it was processed exclusively, is the same, 270 milliseconds each. So how does GVL work? Only one thread can hold the GVL and execute Ruby code at a time. The I/O can be done in parallel, and each thread can run Ruby code for a maximum 100 milliseconds if another thread is waiting. Then it has to release a GVL. Let's see what happens when you process these requests in a Puma worker with two threads. Thread 2 will run for 100 milliseconds. Ruby VM allows each thread to run for a maximum 100 milliseconds. Thread 1 will run for 50 milliseconds in parallel with thread 2, and then wait for 50 milliseconds for the GVL to be released. Thread 1 gets the GVL and runs for 100 milliseconds. Thread 2 goes into GVL wait since it has 50 milliseconds of CPU code still to execute. Thread 1 releases the GVL and goes into GVL wait since it has 20 milliseconds of CPU code to execute. Thread 2 finishes its 50 milliseconds of CPU work. Thread 2 has released GVL because it is now waiting on I/O. Thread 1 executes its remaining 20 milliseconds of CPU code. Thread 1 goes into GVL wait after its 50 milliseconds of I/O. Thread 1 receives GVL and starts executing its 50 milliseconds of I/O. Thread 2 finishes its 20 milliseconds of I/O in parallel. Due to the wait for GVL, we have additional latency in both requests. Rails has also recently lowered the default Puma threads from 5 to 3 due to the latency hit. So Basecamp runs a single thread, GitHub runs on Unicorn, which is process-based, and Shopify runs on Unicorn and Pitchfork to optimize the latency. I'm going to rush through the slides now because the time is up. Second point is memory efficiency. Reforking gives you a lot of memory efficiency. And third is out-of-band GC. So in Ruby, GC is stop the world. That is when GC runs, no code will be executed. It's also generational. So there is minor, major GCs, and minor GCs apply only to young generation objects. And if you survive 3 minor GCs, the objects are promoted to old generation. So minor GCs typically run very fast, and major GCs take up time. And we typically do not want GC to run during a request. So out of band means that you can run GC out of the request. So in Pitchfork, you can have a hook which runs after every request, where you can check whether the major GC needs to be run and then run it. And in the latest Ruby, you can also disable the major GC, and you can just run the GC when it is required after every request. Easier to debug performance issues. Since there is no GVL and there are no pauses due to GCs and no internal queues, it becomes trivial to spot where the performance issues are. It can exit cleanly. So if you can have a hook after every request to see if your worker has exceeded some thresholds, for example, memory, and then just exit it. You cannot do that in Puma because multiple threads might be operating at the same time, so you can't exit cleanly. But since each worker is processing only one request at a time, you can do that in Pitchfork. And timeout. So you can terminate workers which go beyond a certain time limit for requests. And again, since each worker handles only one request, this is a clean timeout, unlike in Puma where it might terminate other threads. Thank you.